Physics from the University of Colorado, and a very prestigious school for astronomy. Um, and I want to talk about one of his more bizarre um, conclusions. So, the video we're going to be looking at is from a speaking engagement that he was involved in at a church, and he was giving five um, evidences, if you will, for a young Earth, and why those evidences he feels are scientific. The last of the evidences that he wanted to present is the has to do with the speed of light, and this is the so-called distant starlight problem. Virtually all astronomers agree that the methods used to determine that stars are light years to hundreds to thousands of light years away from the Earth are pretty sound. The initial measurements were done with simple geometry. Once we had telescopes with enough precision to perform a procedure called the parallax method, where we compare close stars that seem, or at least stars that seem to be close, with stars that seem to be more distant in the background. And so what you do is you take a picture of the sky, the region of the sky, um, during one part of the year, and then half a year later, when the Earth is on the other side of its orbit on the sun, you take another picture and you overlay the pictures on top of each other, and the background stars, the stars that are really, really far away, will not really seem to have moved. Um, and the foreground stars, the stars that are closer, will seem to have shifted a little bit. And if you can measure that shift with respect to the background stars, you can get an estimate for the distance to the system. And you've experienced this more than likely if you've ever been driving and you see a really distant object like a city coming into view or a mountain range or something, and it doesn't seem to move appreciably over the span of a few seconds, whereas any telephone poles or power lines are zipping by you, very, very quickly. So things that are closer to you seem to move faster relative to you than things that are further away. And that's essentially the idea behind parallax. When you shift your position with something really, really far away, it doesn't really seem to move with respect to your point of view, whereas things that are relatively close to you are going to move appreciably, or at least measurably. So that first method is a direct, you don't have to rely on any astrophysics essentially to get that method. You just simply have to trust that geometry works. And that's a much simpler assumption than assuming that or buying into the idea that astrophysicists really do know what we're talking about. So when we talk about the luminosities of stars and measuring those luminosities and so on, then we can get estimates of their temperatures that way, or I'm sorry, their distances that way, that there are relationships between certain types of pulsating variables and their luminosities. And if we can measure their pulsation periods, even if we can't measure their luminosity directly as easily, we can still then infer the luminosity and therefore the distance just from the pulsation periods. But that invokes some fairly um, deep assumptions on the part of astrophysicists that we actually understand to an extent what's happening with the stellar pulsations. We are pretty confident that we do. And in fact, stellar pulsation is my particular field of study. So we're relatively confident in those techniques. And then, of course, you go out further, and the idea that type 1a supernova are going to be relatively uniform in their brightness. So if you can find a type 1a supernova in a deep sky survey, and you can measure its apparent brightness, then you can compare that to how bright it ought to be, and you can get its distance that way. So all these techniques build on one another, and even if you feel for some reason that the long distances may be suspect, let's for example suppose that you don't trust the type 1a supernova method because you're not sure that the luminosities actually are uniform, and that's a valid assumption. That's something that astronomers are checking all the time, actually, as a matter of fact. So there's no problem in being skeptical with that. And I would say the same thing goes for the period luminosity relationship with pulsating stars. That one seems to be a little bit more clean. And then if you really go out, then you can use spectral redshifts to measure distances. Since Hubble's law seems to be true, then if you can measure the redshift of an object, you can plot it on a Hubble plot, and you can immediately read off its distance. So there's multiple methods. And most astronomers, even creation astronomers such as Jason Lisle and Danny Faulkner, agree that these methods are relatively good, that even if there is some uncertainty on the larger distance end, that at the very least the universe is really big and billions of light years across. And so that poses a distinct problem for creation scientists, because when you talk about light traveling, even just in our own galaxy, thousands of light years to reach Earth, the galaxy is 100,000 light years across. So even the stars at the extreme opposite end from us, we're not on the end. We're actually about a third of the way out from the middle of the center of our galaxy. So the stars on the other end away from us would be roughly somewhere around 70 to 80,000 light years away. So even if you just take that, our own galaxy, let alone the Andromeda galaxy, which is a couple of million light years away, and so on, even if you just look at the stars in our own galaxy, you're talking about light having traveled for 70, 80,000 years to reach Earth from the most extreme distant points. And of course, if you're going to hold to an idea that the Earth is only 6,000 years old or so, this poses a problem. And Lyle's attempt to resolve this is simply puzzling. So I'm gonna play, and I'm gonna let it play through most of what he has to say without interrupting him. But then I will offer some of my own thoughts from a physical perspective on what he's saying and what the implications are.
What about distant starlight? I want to spend some time on this one because this seems to be a big problem for a lot of people in terms of embracing what the Bible teaches. It really shouldn't be, but because of the weakness of our faith, sometimes we need a little more. Distant starlight really is not a problem for a young universe. What I'm talking about here is the fact that we can see these galaxies that are billions of...
I lied. I'm going to interrupt very, very quickly. So he just said that distant starlight is not a problem for a young universe. If it weren't a problem for a young universe, there wouldn't be the head scratching and mental gymnastics that we're about to see. And I'll explain why these are mental gymnastics as we go.
Light years away. And when I use the term light year, that is a unit of distance, not time. A light year is about 6 trillion miles, okay? And so when I say the universe is billions of light years in size, that just means it's really big. It doesn't mean it's old. People hear the word year in there and they think that, well, doesn't that have something to do with time? Well, a light year is the distance that light under normal circumstances would travel in 1 year. And so you'd think if these galaxies are billions of light years away, that it would take light, billions of years to get from there to here. And obviously the light has got from there to here because we see them. And so doesn't that prove the universe is billions of years old? And this has come to be called the distant starlight problem. But I want to give you what I think is a solution to this. There's actually a number of different ways to resolve it, which is interesting. And of course, God has access to solutions that we might not have even thought of or even considered. He's not bound by laws of nature as we are. But I do want to point out that some of the proposed solutions really don't work. And I mention this because sometimes people will come up and say, well, have you thought of this? And yeah, we've thought of that. And there's a reason it doesn't work. Some of the simpler solutions that people think of really have been investigated and they don't pan out. The idea that the distances aren't real, maybe the galaxies are all within 6,000 light years, it's not realistic. Even our own galaxy isn't within that distance. These distances, I won't go into all the details, but there's good science to support the fact that these are at incredible distances. The idea the speed of light was much faster in the past, I think that was very worthy of consideration. I'm glad that they looked into that, but I think there's compelling evidence that it was not faster in the past. The speed of light is linked into other properties in nature. It sets the relationship between, for example, between electric fields and magnetic fields.
Okay, so keep in mind what he just said, that the speed of light is linked to other properties in nature. And consider that in terms of what he's also going to propose.
It sets the relationship between energy and mass. And so if you tinker with the speed of light very much in vacuum, it might not even make atoms possible. So we like the speed of light the way it is. Light was created in transit is one that I want to spend a little more time showing you why I don't believe that's a good idea for starlight. People have pointed out, well, the universe was made mature in the sense it was functional. Adam was made as an adult. He didn't have to grow up from a baby. And if you assume he grew up from a baby, you'd conclude the wrong age by looking at him. And that's true. That's certainly true. And so people have said, couldn't starlight be that way? Couldn't it be that God made the beams of light, the star, connecting the star to the earth? I think not. And the reason is because it would require God to create fictional images and movies. And I want to show you what I mean by this. Here we have Supernova 1987A. There was a star in one of the Magellanic Clouds, and that little star right there in 1987 decided to blow itself to bits. Very sad, but it's a supernova. And so that star blew up. Now, this star is in one of the Magellanic Clouds. It's over 100,000 light years away, let's say 170,000 light years away, something like that. And
for context, the Andromeda Galaxy is our closest major neighbor, but our galaxy has satellite galaxies that orbit just like the moon orbits the Earth or planets orbit the sun. And the Magellanic Clouds, which are visible from the southern celestial hemisphere, or if you go south of the equator, you can see them. You can even see them just a little bit north of the equator, but they're best visible in the southern hemisphere. And they are satellite galaxies of the Milky Way, and the Milky Way being about 100,000 light years across. They're a few thousand light years further than that. Away from the center, so yeah, roughly 170,000 light years, give or take. So just for context, he's talking about a satellite galaxy of the Milky Way. Milky Way has about between 100 and 200 billion stars. The Magellanic Clouds thought to be in the range of maybe a billion or so.
And today, it looks like that. We see expanding star guts, what's left of the star expanding off into space. Now, if you say, well, when did that happen? Now, the secularists would say, well, 170,000 years ago, and the light just got here in 1987. And if you say, well, no, the reason we're able to see that is because God made the beam of light already on its way. When did this happen? Well, if you believe in light in transit, this didn't happen. It was just a picture that God made in a beam of light about 6,000 light years out that finally reached the Earth in 1987. If you believe in light in transit, This star never existed. That explosion never happened. And by the way, this doesn't exist either. These are just pictures that God put in a beam of light. And that really bothers me. It's not that I don't think that God has the power to do that. Of course he has the power to do that. The question is it consistent with his nature to do something like that? And I don't think it is. And I don't think God would create, light with fictional information in it, as it were. And if you say, well, I don't know, I think he might, be careful, because how do you know I'm here right now? Right? I mean, how do you know God isn't making the light 1 inch away from your eye, an image of me? Well, we hear you too, no problem. God made the sound 1 inch away from your ear.
This is a classic philosopher problem or philosophy problem. How do you know things exist, right? We very well could have been made just a moment ago, and embedded with all of our memories and all of our experiences and so on, and we would have no way of proving that we weren't created just a moment ago with all of our memories intact. So it's kind of an interesting philosophical puzzle there.
No, I don't think that God makes fictional pictures for us. So if light in transit is true, then none of these things have ever actually existed. But we do see these things. And I think there's a better answer anyway. One of the ones that I thought was a little more plausible, I think it's not the right answer, but I want to mention it because at least it deserves consideration. Dr. Russ Humphreys has pointed out that time can flow at different rates under different circumstances. Einstein discovered that. And Humphreys says, well, maybe that's the solution to Starlight. Maybe that clocks on Earth tick slower than clocks in the universe. And I've chatted with him about this. It's an interesting model. I haven't seen the math work out in a way that actually solves distant starlight, though. But he continues to work on it, and it's interesting. I'm going to suggest that the solution...
Yes, it's possible for time to travel more slowly. The problem would be, right? Time flows. Let me put it that way. Time flows more slowly, gravitationally speaking, when you are near a massive object. So if you want time from all of the entire distant universe to flow more slowly than for Earth, the average density of space out there and the space that the light would flow through once it leaves a galaxy is fairly empty. There is some gravity for sure, but the effects are most extreme when you're near things like a black hole or neutron stars or things like that. When you're really close to the surface of an extreme gravitational object, you can get effects in large galaxy clusters and things like that. But by and large, when you're, a beam of light moseying out of a cluster of galaxies, that cluster of galaxies is not going to have a pull on you the same way that a supermassive black hole would if you ventured too close to it. And so I just don't find it plausible that there would be uniform regions across the entire celestial sphere that we see where light would be uniformly slowed down in time. Or for us, because we're really not a massive object, and so you would need really massive objects in distant space. But we know, and even folks like Lisle and Faulkner will agree that space is expanding, and so the average density is decreasing as time is going on. So you have all of this empty space, so the light's not going to be affected gravitationally that way unless you ascribe to space being much smaller in the past, which harkens back to a Big Bang. And the Earth is just simply not a large enough gravitational object to change the rate at which clocks flow that much when you're talking about, light coming in from hundreds of thousands to millions of light years away. The Earth is not a large enough gravitational object to change the rate for us to be very, very slow comparatively. And so the gravitational time dilation just for now doesn't hold any water.
Solution may involve, I'm going to give you what I think the answer is. I think it involves the one-way speed of light, and that is the speed of light on a one-way trip as opposed to bouncing out off a mirror, a two-way trip. The speed of light in vacuum is 186,282 miles per second, very fast. But that is a round-trip average speed. And what I mean by that is if we wanted to measure the speed of light, here's how we could do it in principle. We could build a very long hallway, okay, 186,000 miles long. We'll pretend we have government funding so we can waste it that way, okay? And we'll put it out there. And so I'm going to stand over here on this end with my flashlight. I'll have a mirror at the other end, or another flashlight, either would work. And what I'm going to do is when the clock strikes noon, I'm going to turn on the flashlight for just an instant, send that pulse out, and it'll reflect back. And as soon as I see the reflection, I'm going to look at the clock and see how much time has elapsed. And if we were to do this, we would find it takes 2 seconds for light to go out and come back. And so it's traveled a distance of 186,282 miles twice, and it's taken 2 seconds to do that. So the average speed is 186,282 miles per second. That's how you get the speed of light, and that's what we would find. Most people assume that it took 1 second to go out and 1 second to come back. But we don't actually know that, do we? All we know is the total time is 2 seconds. It could be, hypothetically, the case that the light zips out and takes all of 2 seconds. Maybe it takes no time at all for it to get out there, and then it takes all of 2 seconds to get back. That's a possibility. Or maybe it's the reverse. Maybe it takes all of 2 seconds to travel out there, and then it zips back instantaneously. And people have said, well, why? Is the mirror affecting it? No, it doesn't have to be the mirror. You could even use another flashlight out there. And when your buddy sees the beam, he turns on the return trip. It could just be that the nature of space is such that light propagates at a different speed this way than it does that way. You'd say, why would it be that way? Well, there are certain crystals that do that, where the speed of light's very different in one direction than another. And it could be that the vacuum of space is like that.
Okay. We do have crystals where the speed of light travels faster in one direction than another direction. This is due to the lattice nature and the way the crystals are structured, and also depends on how you orient the beam of light going into the crystal as to how the crystal will affect the beam of light. As far as we know, space is not structured like this. Okay, I should say space-time, because we're now in the realm of Einsteinian relativity. Space-time, the fabric that light propagates through in space is, as far as we know, we have no evidence. And this is a refrain that Bill Nye, of course, kept saying on the Ark over and over again with Ken Ham. Sir, we have no evidence for this. We have no evidence. And we don't have evidence that the beam of, or that light is affected in any way by the direction of propagation. We just simply don't have any evidence. And so he's going to make an interesting claim here in just a moment. And I'll talk about the evidences that we don't have, and the evidences that the one-way speed of light could imply. And so, yeah, we'll keep watching.
Point is, we don't know. And you see where I'm going with this, because if this is the case, if light, when it's moving away from me, is slower, and when it moves toward me, it's much quicker than the average speed, that would solve the distant starlight problem, wouldn't it? because I don't have to send light out to the galaxies and reflect it back. It only has to make a one-way trip. It only has to go from there to here. But so I'm hoping that this will be the case, but hoping for something doesn't make it so. We want to see if we can do an experiment to measure the one-way speed of light. So how are you going to do that? How are you going to measure the speed of light just on a one-way trip and not a round trip? Well, you can't use a mirror anymore. Instead, you got to use two clocks. You got to use one clock to tell you when to start the light pulse, and then another one to record when it impacts. Yes? So I'm going to stand over here. When this clock strikes noon, I send out the pulse, and my buddy's over there with his clock, and when he sees the pulse, he looks at his clock, and you're thinking that'll say, 1 second past noon. Yes? Well, I tried this in my office. I don't have a long hallway, but I have the distance between my watch and the clock on my phone, and I turned on the light right when it hit noon, and the light beam went over to the phone. As soon as the phone, lit up, I said, 12:05. It takes 5 minutes for light to get from my watch to the phone, right? No, you're not buying that? You see what I'm saying? When my clock hits noon, I turn on the light, it goes over, hits the phone says 12:05, 5 minutes. I made an assumption, didn't I? A faulty assumption. And that is, I assumed that the clocks were synchronized. Obviously, the clock on my phone is 5 minutes fast. I do that so I don't miss staff meetings. Okay, so only if the clocks are synchronized could you measure the speed of light this way. And by the way, they have to be exactly synchronized because the speed of light is very quick, whatever it is. We know it's quick. So if that other clock is just a little bit off, you'll get the wrong answer for the speed of light. It could be very wrong. You say, no problem. We'll make sure the clocks are synchronized. That turns out to be very difficult to do with clocks that are separated by a distance. Normally, the way we synchronize clocks is with a radio transmission. In fact, my watch does that. It receives a signal from the radio transmitter in Fort Collins, which is tied into the atomic clock in Boulder, and every night it receives that signal. I never have to set it. It's pretty neat. But it's not maybe exactly synchronized, right? Because that radio pulse actually takes a little bit of time to travel from the source clock to the receiver clock. Radio is fast, but it's not instantaneous. So, maybe what we could do, of course, if we knew the amount of time it took the radio pulse to travel from here to here, we could subtract that off. We could push that clock forward a little bit. Well, how fast does radio travel? You know the answer to that? It travels at the speed of light. Yeah. And so that's the very thing I'm trying to measure. That's the very thing I don't know is the one-way speed of light. We know radio travels at the speed of light because if I have a radio transmitter and a flashlight, they'll hit the wall at the same time. We know that. We just don't know what that speed is. My point is you'd have to already know the one-way speed of light in order to synchronize clocks by radio transmission. Now, I don't worry that my clock is maybe slightly behind the one in Boulder because I'm not trying to measure the speed of light. But if you're trying to measure the speed of light, they have to be exactly synchronized. Some people, for some reason, have thought if you put the radio transmitter in the middle, that'll solve it, right? Because then you send the radio pulse in both directions, and both clocks are synchronized to noon at the same time. It doesn't matter what the speed of light is, but in fact it does, because that presumes that the speed of light and therefore the speed of radio is the same in both directions. If it's different, then this clock gets set to noon first, and that clock gets set to noon second. See, noon there, and then noon there. And they're not synchronized. See, so you can't synchronize clocks that way. It doesn't work. One last resort. We'll synchronize two clocks in the same place.
You can synchronize clocks that way if you aren't trying to make this assumption, okay? Again, we have zero evidence that you cannot synchronize clocks that way. You can't synchronize clocks that way if you assume that the one-way speed of light is variable. That's true. But again, in practice, no physicist would hesitate to actually synchronize their clocks that way, unless they were trying to design an experiment for this purpose.
That's easy to do because you can see they're both reading the same time at the same time. Then we'll move one of them or both of them to opposite ends of the hallway. Yes? That should work, right? It doesn't, because according to Einstein, motion affects the passage of time. The very act of moving the clock has caused it to become desynchronized from its buddy. Now, it turns out there's an equation that can tell you how much the clock has become desynchronized, and you could compensate for it. And in that equation is The speed of light. Yeah. Isn't that interesting? It's almost as if God doesn't want us to know the one-way speed of light. Here's what the implication of this is. Apparently, it's impossible to synchronize clocks without knowing the one-way speed of light in advance. And it's impossible to measure the one-way speed of light without synchronized clocks. So you see, we're stuck in a permanent catch-22. It is fundamentally impossible to measure the one-way speed of light. It cannot be done because you need to have synchronized clocks. And the only way you can have synchronized clocks is if you already knew the one-way speed of light. It cannot be done. Now, when you have a catch-22 like this, it suggests that the question may be a bad question, a faulty question. And so I'm going to conclude that the one-way speed of light is not actually a property of nature at all, but is something that is a convention. A convention is something that we choose, and we all agree to it, and we stick with it, and it works. Like driving on the right side of the road. That's a convention. We all agree to that, and it works. But in other nations, they pick the left side of the road. And as long as they...
So this is a very troubling thing. And we'll dive a little bit more in here in just a moment. But it's true. You can... you can define this convention however you choose. You can define the convention for the one-way / two-way speed of light problem however you wish. But you should let nature and experiment and observation be your guide. So what he's basically claiming here is that because we can't measure the one-way speed of light, that we should ignore it as a property of nature and just agree that it's a convention that the two-way average speed of light turns out to be 186,282 miles per second. I will suggest some reasons why this is probably not a very good conclusion. Again, we can't prove this false, okay? But we can strongly suggest reasons to cast doubt on this as a valid conclusion.
They all agree to it, it works too. You see, that's a convention. It's not, it's, if we asked, well, what, in the universe, what is the correct side of the road to drive on? That question is meaningless because it depends on what country you're in. It depends on where you're at. Or how many, if I had a table that's, let's say it's 1 yard long or maybe it's 3 feet long, which is it? Is it 1 or 3? What's the right answer? Is it 1 yard or is it 3 feet? What's the answer, right? It's both, isn't it? Well, should the number be 1 or should it be 3? Well, you tell me what you want. You would tell me if you're using yards or feet, and I'll tell you what the answer is. The one-way speed of light is like that. We get to choose what it is, and that tells us how to synchronize our clocks. And then when you measure the one-way speed of light with your synchronized clocks, you'll find it was whatever you chose. Yeah. Okay? So the lightning bolt strikes exactly in between these two clocks, and we're going to decide that the speed of light's the same in both directions. We can do that. We're going to choose that, and then the two clocks are synchronized. But if you want to make a different choice, you can do that too, and you can synchronize them differently. That light requires the same time to traverse the path A to M as for the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. We choose the one-way speed of light, and that tells us how to synchronize clocks. And that quote is by Albert Einstein. Einstein recognized that the one-way speed of light is not something you measure, it's something you choose. Which means I can choose it to be something very different than what most people do. In fact, I can choose the speed of light to be infinite when it's directly toward me and half c when it's moving away. And the reason I pick those...
So let's be very clear. What's happening right now is that he's taking this convention of saying, okay, I'm just simply going to assume for the sake of simplicity and to solve my problem that the one-way speed of light might be infinite in one direction and half of the average speed in the opposite direction. but he's going beyond, okay? Because when you make this argument, you're not actually just going into the laboratory and adjusting your clocks based on this convention. What he's trying to do is impose this convention on the universe in order to solve the distant starlight problem. What this means is that he's actually suggesting that this is a property of the universe, that the speed of light is different in its different directions, one way versus the reflected way. Um, and so if you just stick to the realm of convention and saying, okay, this is how I want to synchronize, two clocks in the laboratory, okay. But when you extend this into an anisotropic synchrony convention, as it's so called, the ASC, and use it as the solution to the distant starlight problem, you're actually claiming that this is the way the universe operates. This is a property of nature. And again, we simply don't have any good evidence that this is true. And we'll discuss why.
Those two values, it has to average to c. It has to average to the speed of light. That's the round trip speed. Okay, but you get to pick the one-way speed, and then the average will tell you what the return trip has to be. And it turns out it's 1/2 c if you make it infinite in one direction, because it's a time averaged.
Speed of light is infinite when directed toward the Earth, and half of the average speed of light when it's directed away. Where to begin here? What does directed toward the Earth mean? Lisle knows that velocity is a vector, and in mathematics, vectors carry components. So if I were to direct a beam, say from the moon, but toward the Earth's north pole and not toward the center of the Earth, what component of that speed of light's vector would be affected? He might explain this in some technical papers that I haven't seen yet, but so far I haven't seen an answer to that question. Is this dependent on specific observers on the Earth? Because, for example, I can shine a beam that is, say, a beam from Denver towards Seattle. Okay? If I shine a beam away from Denver and towards Seattle, then that beam is directed both away and toward the Earth. It's away from people on Earth in Denver, and it's toward people on Earth from Seattle. And you can argue, okay, the curvature of the Earth would stop the beam, and so therefore it's directed toward the Earth. But what he's really getting at is that this is observer dependent, is really what he's getting at, that this is observer dependent. And so you would measure the speed of light, if you could measure it one way. What he's suggesting is, let's assume the Earth were flat, which of course it's not, but if you shined a light from Denver to Seattle, the folks in Seattle would measure it, one of those groups would measure it to be infinite, the other group would measure it to be 1/2 c. But again, of course, his whole argument is you can't measure the one-way speed of light, and that's true. It's very, to date, no one has come up with a satisfactory experiment to measure the one-way speed of light. But what we can do is do the same experiment in different orientations. So his experiment with the flashlight and the mirror, right? What if you rotated it 90 degrees? Would the results be different? Um, and we just simply don't have any evidence that this is true. And you can say, okay, but light is so fast that it would, be different. Okay, but again, as he mentioned, we have crystals where the speed of light is variable in direction. We also have crystals where we can actually track the beam. We actually have cameras that are fast enough and crystals that are so dense that we can actually watch the beam move in one direction. And so I would propose take a laser beam and take such a crystal, um, usually really hard diamonds or things like that, and shine the laser beam through a prism of such a material and measure the speed of light in that material, and then rotate the experiment by 90 degrees in the laboratory and do it again. And keep going around the room, and then orient it up, and then orient it down, and you can actually track the motion of the light. And some would say, okay, yes, but for the light to reach your detector, it would have to leave the crystal, and then you're still not measuring the one-way speed of light. But if it were directionally dependent, then it would still manifest itself by moving faster through the material. And as the light was able to leak out and seep through to the detector, the same way that when you shine light through water, you can actually, like if you shine a laser beam through water, you can actually see the beam going through the water. But that beam is the laser beam is going in one direction, and then the particles in the water are scattering it, so then it's kind of spreads out a little bit, and some of the light escapes, hits your eye, and that's the beam. Same thing when you do aerosols with laser beams, and so on. And but the point is, if the speed of light were different in a given crystal depending on how you oriented it, um, you would be able to see it in the crystal, and whenever the light left the crystal, would travel to your eye, and hmm, I just had a thought, but it still wouldn't measure the one-way speed of light, so I won't go down that rabbit hole. But the point being that no matter how the light left the crystal and then got to your eyes or to your camera, or whatever kind of detector you were using, you would still be able to see the speed manifestly different in the crystal, given the speeds that we've been able to reduce the light down to. And there are some more interesting objections. Okay, so first things first, just a little bit about what we understand light to be. Okay, so light is nothing, as far as we know, but oscillating and alternating electric and magnetic fields. And the way that they oscillate dictates the direction of the propagation of light. Now, electric and magnetic fields, okay, um, oh, where was it? It might have been up here. The equation that I'm looking for. No. Gonna have to. We'll go to the next page. Yeah, I think it's down here. Yeah. Um, you can go through a derivation with Maxwell's equations, Gauss's law, Faraday's law, Ampere's law, and Gauss's law for magnetism. And if you assume that you're in a vacuum, you can go through a long and laborious derivation, but you'll ultimately come up with this result. C is equal to 1 over the square root epsilon naught times mu naught. And these two constants, epsilon naught and mu naught, are the permittivity of free space and the permeability of free space. And epsilon naught is sometimes called the electric constant, and mu naught is called the magnetic constant. And these constants just basically define how uh, well or easy it is for electric and magnetic fields to propagate through space. We have zero theoretical and we have zero experimental reasons to assume that this is variable in a given direction. Um, if it turns out that it is, I would love to see such an experiment that actually demonstrates it. You would have to know the one-way speed of light to do it, but there are some implications for what Lisle is talking about that don't require the one-way speed of light. Number one, the energy in E equals mc squared. When you release energy by changing matter to energy, um, that's not a directionally dependent thing. Now, you could still argue that C in that would be the average between both ways, and you would still get the same result. But if it's absolutely true, what Lisle is suggesting, that the speed of light is infinite in one direction and half in the other, then it would be interesting because that means that there is a set way in space time that epsilon naught and mu naught are embedded in the fabric of space time such that it's infinite in one direction and impeded in the other direction. And that direction just all happens to be centered on Earth. And for a creationist, you can say, well, Earth is the pinnacle of God's creation. But most scientists would recoil at the idea of such anthropocentrism. Um, we generally don't like to ascribe to the idea that the Earth is special um, as far as the laws of nature are concerned. We do know that we're special in that we have an extremely habitable planet and seem to have hit the jackpot in a number of areas. And that bolsters a lot of people's faith, and that's fine. But we generally don't like to say that the Earth is special because we're on it from a laws of nature point of view. Now, it could be possible that it's true, but we don't have a good reason other than religious motivations to suggest such. Um, and so we generally try to stay away from that form of argument. But what this equation, C is equal to 1 over epsilon naught mu naught square rooted, implies by itself is that the speed of light is the same everywhere. It doesn't matter what direction it propagates in. It doesn't matter what direction we move in. And part of Einstein's postulates in special relativity center around the idea that the speed of light is constant. That's one of his postulates. Now, again, as we just saw, um, he's basically kind of defining it as a convention in order to achieve simultaneity between synchronized clocks. But um, we have all of the evidence that we do have, I guess I should say, suggests that it's true that the speed of light in all directions is the same. We don't have any evidence whatsoever that it's variable. And here's some things to consider when talking about these kind of things. Um, and by the way, here are the values in SI units for the epsilon naught and the mu naught. 8.85. Um, uh, it won't let me de-highlight, but 8.85 times 10 to the negative 12 coulombs per meter, coulombs per newtons times meters squared, and 4 pi times 10 to the negative 7th Teslas times meters per amps. And so, uh, yeah, again, we just don't have any evidence to suggest that the speed of light is variable in one direction. And here's some things that I would suggest, and actually we'll talk about these early attempts to measure the speed of light. Actually, I'll probably put these in the next video. But what I really want to get to is what's known as the Compton Effect. And so what we see here is that the energy of a particle, okay, the energy of a particle, be it a massless photon or be it any other particles, follow this form. Okay, the energy is equal to, well, the square of the energy is equal to the momentum squared times the speed of light squared plus the rest mass squared times the speed of light to the fourth. And if you don't have any momentum and you're simply at rest, then this reduces to E equals mc squared. Okay. But the momentum of a photon, okay, so photons, even though they're massless and they're traveling, they have momentum. And we've actually measured how much of a kick they can give to objects. So, and this is the principle, and we've even demonstrated this in the laboratory, that you can use large conducting foil sheets as solar sails. So if you want to, put a spaceship and you don't want to use regular fuel to launch it vast distances, and you're okay with slow accelerations, then just build a large solar sail and let it collect sunlight. And as the photons from the sun come in, they'll bounce off of it and they'll keep pushing it and they'll keep pushing it and pushing it and so on. So we know that light has momentum, and light has momentum according to this equation. Okay, so the energy of a photon is equal, or the momentum of a photon is equal to its energy divided by the speed of light. And we can use Planck's equation to show that the energy is equal to Planck's constant times the speed of light divided by the wavelength. And this ends up with what ultimately will become the de Broglie hypothesis, that the momentum is equal to Planck's constant divided by the wavelength. And de Broglie applied that. Einstein derived this for photons, and de Broglie then applied that to actual particles with mass like electrons and protons. in the development of quantum mechanics. But the point here is that photons carry momentum, and this is seen very clearly in experiments like the Compton Effect. So the Compton Effect is when you have a light source that has a glancing collision off of an object and then is scattered. And when you shrink this object down to the size of particles, like protons and electrons, you can actually measure. If say you have a gas cloud chamber, you can actually see the path of a charged particle, and you hit a beam of charged particles with electromagnetic radiation, you'll actually see them deflect. You'll see the particle beam deflect. And so what's happening is the collision is it's an elastic collision, and the momentum from the light beams is being in part transferred to, I should say, the momentum is being exchanged between the photon and the particle. And what happens is you can actually predict where you should put your detector to find the particle. And it's a very simple result when you go through the derivation. And the Compton shift is written as the change. Not only are you shifting the direction, but you're changing the wavelength as well. Because some of the energy and momentum have shifted, therefore the wavelength has shifted. And so you can find how much the wavelength has shifted if you can measure the angle that it's been scattered at. So here's where I'm driving with all of this. If the speed of light were variable if the one-way speed of light were variable, and to use his convention, it's infinitely fast coming toward us, and half the average moving away from us. You could orient an experiment like this, where you have a beam directed toward the ground and your particles toward the floor, and do this experiment, and then shoot the beam up and have your particles above you. And you should measure two different results, because if the momentum of a particle is dependent on the speed of light, the momenta are going to be very, 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 very different. And if you hit a particle with a beam, with a photon, for example, that's traveling infinitely fast, it's going to give a much different kick and a much different signal than if the photon is traveling at 1/2 c or even c. And so, given that we have performed all of these types of experiments in all sorts of orientations in different labs all across the globe, and they've all come up with the exact same results each time, we simply don't have a reason to conclude or assume that the one-way speed of light is any different than the two-way measured speed of light that we see. It's actually kind of interesting. I suppose I will talk about it for a moment. Let me come back here. I wanted to. This isn't where I wanted to be. This is where I wanted to be. Let's come back up here. And here. find it again. I've got too many tabs open up here. Um, Here it is. Yeah, here it is. So the early speed of light measurements. Um, this is kind of interesting because this is almost a one-way speed of light measurement. Okay, this was the first time an experiment was done with enough precision to actually say that the speed of light was finite. Okay, and so here's what happened. This was done by a Danish astronomer named Ole Romer, and the idea is that if you can measure um, the times of eclipses of Jupiter's moons at different points between Earth and Jupiter's orbits. So at one point in time, Jupiter will be a little bit further from us, and at another time, Jupiter will be a little bit closer than us. So ever since folks had been using Jupiter's moons as a device to measure longitude. Okay, so explorers would rely on astronomical tables for noting where they were. And your latitude is easy enough, especially if you're in the northern hemisphere. All you have to do is find the North Star and measure its angular position above the horizon. You can get your latitude very, very quickly. Um, but longitude is a much more difficult issue. And so, what would happen is astronomers made tables of predicted times when Jupiter's moons would fall behind the planet, and you wouldn't be able to see it anymore. Um, they would be occulted, if you will, by Jupiter. And if you could compare the time on those tables, which was based on when someone in at the Greenwich Observatory in England would see them, and then measure your time when you saw it, you could then work out how many time zones away you were from Greenwich, England, and you could find your longitude. And so Ole Romer, okay, did this um, and noted that there was a difference, okay, between the predicted time at a particular location and when it actually occurred. And he inferred that this was a light time effect based on the fact that Jupiter was in a different position with respect to its orbit as opposed to its average position, which is when the tables were, how the tables were derived based on Jupiter's average distance from Earth. And he noted that there was just an ever so slight difference in the time that he observed certain moons going behind Jupiter versus the predicted times. And so this wasn't a time zone issue. He reasoned that this was a Jupiter Earth orientation issue and that this was indicative of a finite speed of light. And so then he found the tables for where the planets ought to be relative to one another and calculated the distances between Earth and Jupiter at those two different observations, and then was able to come up with a estimate for the speed of light. The amount of time that it took for the extra amount of time, I guess I should say, that it took for the light to get to Earth when Jupiter was further away. And so this is almost right. This is actually fairly close to a one-way measurement of the speed of light. You're not relying on light to reflect off of a mirror, and so we're not timing how long it takes for light to leave the sun, bounce off Jupiter, and get to here. we're measuring the amount of time it takes in difference for light to leave Jupiter and reach Earth in one orientation versus leave Jupiter and reach Earth in another orientation. And so this is pretty close to a one-way speed of light. And if light were infinitely fast toward us, this experiment would not have yielded any results. We wouldn't observe light time effects for things like eclipsing binary stars or taking the light travel time differences into account for orbiting telescopes as they're orbiting the Earth, and the amount of time it takes, or the exact time it took a picture. But based on where that space telescope is in its orbit, it might be in a slightly different position than a different picture. And so you actually have to account for those differences, those light time effects, when you are correcting the times or stating the actual times of those observations. And so it's all of these types of things. We don't see differences in how the momenta of electromagnetic radiation changes when it collides with things. We don't see that as a directionally dependent issue. Probably one of the most stark experiments that might be recalled from this would be the Pound-Rebka experiment that measured the gravitational time dilation effect. And in that experiment, they went to a tower at Harvard University and put a plastic tube up and filled it with helium to keep regular atmosphere particles out, and shot X-rays both up and down toward detectors, and those detectors received the particles. And one of the things that the detectors relied on was known as the Mossbauer effect, which allows for a crystal lattice to absorb the momentum of particles without much recoil, right? So it's almost like the entire lattice absorbs the momentum and you don't get the recoil. And so they would measure the energies at which that happened, and both directions, and they were able to show that the wavelength of light changed when you were going toward the Earth versus when you were going away from the Earth. And the light coming toward the Earth was redshifted, and the light moving away from the Earth was blue shifted. And this basically demonstrated that the time for the photons was changing as they experienced the change in the Earth's gravitational field. And if their speed were infinite in one direction, then the momenta transferred to the crystal lattice detectors would have been, the signal would not have looked like it did. I'll just put it that way. The signal would not have looked like it did. And I have one more objection to this, and that is that we can make these kinds of measurements at all. We rely on telescopic images of light coming into our telescopes, and older telescopes relied on the collection of light with glass plates. Newer telescopes rely on CCD cameras, the same as the cameras on your iPhone. There's a chip with little regions called pixels, and the light comes in and hits that pixel and transmits an electrical signal to the computer, and then the computer translates all of those pixels and the information that those pixels contain into an image. And if the light were coming in infinitely fast, it would destroy the pixels on CCDs because the light would have infinite momentum. And you can argue, well, but there's at most astronomical telescopes involve mirrors. So you have a mirror reflecting. So, like if your telescope tube is like this, your light would be coming in, it would bounce off of a mirror, and then it would bounce off of another mirror, and then it would bounce to your detector. So then I would ask, okay, so you're going to say that the mirrors do something that would cause the momentum to not be infinite, so that when they hit your pixels, they don't destroy your camera. But what about refractor telescopes that don't have that? That the light just interacts with essentially two lenses and the camera. Um, you can argue that perhaps the lenses do something to slow down the light, but again, if the light had infinite speed and momentum in one direction, um, that should effectively shatter your lenses on your telescopes. So we just don't have any evidence to suggest that epsilon naught and mu naught are directionally dependent. If and when robust evidence to suggest it comes in, I'm all ears and I'm all open. But for the moment, this is really a stretch on Lisle's part, to simply try and make a conclusion with some really stretching of the facts science to make it fit in the box that he wants it to fit in. This is not a case of somebody allowing nature to speak for itself. This is somebody trying to force nature to say something that we don't have any evidence for. And that is why I claim that creation science is not science in the classical sense. And if you will, that is why I am pursuing these videos. Um, I would like to take a moment in closing here and say that I am not tone deaf to the events that are going on in the world right now. And as Ukraine is being invaded by Russia, um, and other wars that are happening around the world, I just want to take a moment and express my solidarity with the Ukrainian people who have been attacked unprovoked, for the loss of both Ukrainian and Russian life that didn't have to be lost, and my deepest and sincerest hopes for a quick and swift end to